Hello, this is Stat 134, Lecture 7. Last time we covered Section 2.4, Poisson approximation to binomial, and we saw that Poisson is a limit of binomials for large n and small p as np goes to mu. So this is important because we know a lot about binomials, and hence we inherit a lot of knowledge about the Poisson. For example, we know that the mode of binomial is the floor of np plus p for non-integer np plus p. So this translates to knowing that the mode of Poisson is the floor of mu for non-integer mu. Today we're going to do section 2.5 on random sampling. It comes in two flavors. You can sample with replacement and without replacement, and each of those have their generalizations. So for drawing with replacement, we of course know the binomial distribution, which generalizes to the multinomial distribution when you have more than two outcomes in your trial. Or for the dependent case, the analog of the binomial distribution is the hypergeometric distribution, and its generalization is called the multivariate hypergeometric distribution when we have more than two outcomes in our trial. So let's start section 2.5, sampling with replacement. We have a class of 100 students, 50 A's, 30 B's, 15 C's, 5 D's. We sample 10 students and want to know what's the probability of our sample having 4 A's, 3 B's, 2 C's, and a D. So the strategy is let's write out our students in order. So we have 10 students, and I'm going to assume that A's followed by B's, followed by C's, followed by D's. So the probability of that happening is 0.5 to the fourth power times 0.3 cubed times 0.15 squared times 0.05 to the 1 because, well, we have the multiplication rule and we have independence because we're drawing with replacement. Now, there's no assumption that A's have to come first and so on. So we're going to multiply this by 10 factorial, but then we need to divide by 4 factorial, 3 factorial, 2 factorial, 1 factorial to deal with the 4 A's, 3 B's, 2 C's, and a D. Now, all these factorials, we can write that in a nice expression that sort of generalizes choose. So call it 10 choose 4, 3, 2, 1. So out of 10, we're choosing 4 A's, 3 B's, 2 C's, 1 D. And this is a generalization of choose when we usually write, for example, 10 choose 4. You could write that in this way as 10 choose 4, 6. Now, the multinomial distribution is a generalization of the binomial distribution. Here, what we have is 4 possible outcomes, each with its associated probability. And so the probability that you have N1 of the first possible outcome and N2 of the second, and so on, we have a formula here that just follows analogous to the binomial formula. Now, when we sample without replacement, let's take a look at this. So here, say that we only have 2 types of students in the class. It's a very happy class of A's and B's, and I'm drawing 5 students at random without replacement. That's called a simple random sample, or SRS. So find the probability that we have 3 A's and 2 B's. So I'm going to proceed exactly like before. I have I write out in order my 5 students. I have A's followed by B's, let's say, and then the probability of that would be 70 over 100 times 69 over 99 and so on, just the multiplication rule here, where when I write 69 over 99, that's the conditional probability that where I'm conditioning that the first student is an A. So now there's no need to assume that 3 A's are followed by the B's, so I need to multiply this by 5, choose 2, and that's your answer. So now I just want to make note that had we drawn with replacement, then this would have just been exactly a binomial formula application, and you would have gotten 5 choose 2 times 70 over 100 cubed, 30 over 100 squared. So it's really the same thing. And when we're doing it this way, what is our sample space? Our sample space are, we have a 5 tuple, you can think of it, or you have an ordering of 5 things, right? So what does 100, 99, 98, 97, 96 mean, right? So there's 100 ways that I could choose the first student. There's 99 ways I could choose the second student, and so on. That's what your sample space is. So what we can do, however, is you could change your sample space, and instead of having a 5-ordered tuple, you could say that, you know what, I don't want ordering to matter here at all. So I'm going to divide this 100 times 99 times 98 times 97 times 96 by 5 factorial. If you do that, you're saying, you know what, order doesn't matter. So let's do that. Now if I do that, so that's what in the equation on the right here, I also need to do it in the numerator, right? So the A's, I have to divide by 3 factorial because the ordering doesn't matter, and I have to divide the B's by 2 factorial in the same way. And the math just works out amazingly. So you can just see that you're going to get the same answer. It is an equal sign here. And this leads you to a very nice formula, which is that in the denominator, we have 100 choose 5. So out of 100 students in the class, what are all the ways that I can choose 5? That's what your sample space is. And then the probability, the event that we're looking for is the chance that out of 70, I choose 3, and out of 30, I choose 2 B's. So this is called the hypergeometric formula. So this is the general hypergeometric distribution, where we have a population of size capital N containing capital G good, capital N bad. N is G plus B, and your sample size, little n, has little g good and little b bad elements, so little n is G plus B, is chosen at random without replacement. So the probability of having G good and B bad is, so in our denominator, it's out of our population size capital N, we choose little n, and in our numerator, our event is out of capital G good, I'm choosing little g, and out of capital B bad, I'm choosing little b. So this generalizes to the multinomial this generalizes just like the multinomial distribution. It's called the multivariate hypergeometric distribution. And so instead of good and bad, let's say I have k flavors of good. And in my sample, I'll indicate that is small g1 up to small gk. So you have just an analogous formula. So let's use this and redo our first example. So now we're drawing without replacement from these students. And so the answer will be just what you would think. So let's look at a 5-card poker hand consisting of a SRS of 5 cards from a 52-card deck. So there's 52 choose 5 poker hands, right? Because in a poker hand, order doesn't matter. I'm just kind of holding the cards together. There's no significance to the order of the cards themselves. So the probability of a poker hand having 4 aces and a king, so by the multivariate hypergeometric, so that would be, so my 52, of my 52, remember that I have 13 different ranks, each with 4 cards. So I have 4 out of 4 aces. I have 1 out of 4 kings, and the rest of the ranks I'm choosing 0 from. So notice that all the numerators all the numerators 4, 4, 4, 4, they add up to 52, and all the denominators 4, 1, 0, 0, 0 add up to 5. Now 4 choose 0 is 1, so I usually don't write those. So let's just write it the way I've shown here. So next, let's find the probability that you have a poker hand has 4 aces. So now the single card can be anything. It doesn't have to be king. There are 12 other ranks that it could. There are 12 ranks that it could be, right? So I have to multiply my answer above by 12. If I want to find the probability that my poker hand is 4 of a kind, in other words, has rank A, B, where here A and B are different, then I have 13 choices for A and 12 choices for B. Now, then we did a concept test, and Uncle Adam messed it up. There was a misprint here, and you guys did a great job despite of me. Here is actually the question I meant to ask. And many of you thought that the answer is B because you're thinking to yourself, oh, okay, there are 13 possible A's, there's 12 possible B's, and there's 11 possible C's. Well, the thing is that, no. So we're double counting here, right? Because in my poker hand, AAABC is the same as AAACB. So the order of the singleton there doesn't matter. And so 12 times 11 should actually be 12 times 11 over 2, which is really 12 choose 2. So the answer is C. Just to test your understanding, what's the chance to get a pair? So here, your poker hand has ranks A, B, C, and D, where A, B, C, and D are different. So here, there's 13 choices for A, but then we want 12 choose 3, right? So of the remaining 12 ranks, I'm choosing 3. So where order doesn't matter, right? And the order doesn't matter because this is a poker hand. So AAA, BCD is the same as AAA. Oops, sorry, I have too many A's here. Oops, okay. Well, you know what I mean. So I really wish you guys have a great weekend, and I will catch you guys on Monday.